So good evening, everyone. Thanks very much for coming. So it's been maybe 20 years or so since lots of computer scientists started getting interested in game theory and economics. And that's because at that time, in the late 90s, that's when the internet was becoming widely adopted and commercialized. So a lot of the emerging applications in computer science at that time really called out for game theoretic reasoning because they involved the interaction of multiple parties with conflicting objectives. Everything from competition between internet service providers and network routing to the design of real-time auctions for online advertising like those that now drive the business models of companies like Google and Facebook. But something interesting has been happening in the last maybe 8 to 10 years, which is that ideas have increasingly been flowing in the opposite direction, from computer science to game theory and economics. So this talk is meant to be a detailed case study on that point via a really major auction that was run in country and concluded last year, involving tens of billions of dollars and in which, as we'll see, computer science played a really vital role. So our story begins back in 2012. That's when Congress authorized the FCC to design and deploy a novel kind of auction. And the point of the auction was to sell spectrum licenses, licenses for the right to use certain frequencies in certain areas. Now, it wasn't actually a new idea in 2012 for a government to use auctions to sell spectrum licenses. They'd actually been doing that since the early to mid 90s. What was different in 2012 and what necessitated a novel auction format is that for the first time, the spectrum that they really wanted to sell, the part that would be juiciest for wireless broadband and other emerging applications, was inconveniently already accounted for. There were already parties who owned licenses for that spectrum, the parties being over-the-air television broadcasters. So this is actually going to be a double auction with both buyers and sellers, and the goal is to repurpose spectrum, to procure it from those who are not getting very high value for it, and then to sell it to those who can get much higher value. So the auction is going to have two phases, a reverse auction and a forward auction. The reverse auction is when the government is in buyback mode. So the participants in this auction are going to be the current owners of these licenses. Again, over-the-air television broadcasters. And the government's going to be paying them money for the right to reclaim their licenses. And this is the part of this auction which was completely new. Literally no reverse auction like this had ever been run like this before this FCC incentive auction. Then there's the forward auction, which is once the government has successfully procured all these licenses, it turns around and sells them to the highest bidder. So here the participants are typically telecom companies, T-Mobile, AT&T, and so on. And again, forward auctions is what they had been running since the 90s. So the auction concluded in March 2017. It ran for about a year, so it ran for quite a while. So it ended last year and the dust has settled, so we can see how it did. And certainly by some measures, it did pretty well. So the government did spend $10 billion procuring these licenses in the reverse auction phase, which sounds like a lot, except that the government was able to actually sell those licenses for $20 billion in the forward auction part. So the auction cleared $10 billion. And even after covering the auction's costs and a couple other earmarks, there was still a ton of windfall left over, and that was applied against the US deficit. That was actually the plan all along, which is maybe one of the reasons the bill didn't have much trouble passing a very partisan 2012 Congress. Maybe another reason had something to do with the name of the bill. Remember, this is a bill that authorized the design of an auction, but they called it the Middle Class Tax Relief and Job Creation Act. I dare anybody to vote against that. Okay? So my plan for the talk is to spend about half of it on the reverse auction, and this is the part where it's totally new and computer science played a vital role in which auction got deployed. But I'll also spend half the time talking about the forward auction, where we'll see that the theoretical computer science toolbox gives you exactly the right language to explain when forward auctions work well and why. So let me tell you a little bit about how this reverse auction works. So the auction format was proposed by two economist colleagues of mine at Stanford, Paul Milgram and Ilya Segal. It's a format known as a descending clock auction, which can be thought of as extending previous formats in both the game theory and computer science literatures. And really the biggest design goal of this auction format was to make it as easy as possible for the participants in the auction. Remember, in the reverse auction, the participants are over-the-air, often mom and pop television broadcasters, okay, perhaps with zero experience with auctions whatsoever. So they wanted it to be really easy for them to participate in. So with that in mind, I'm gonna tell you how it works. So it's an iterative auction, runs in rounds, and in a given round, if you're a remaining participant, if you're still in the auction, you might be asked a yes-no question, okay, of the following form. Would you or would you not be willing to sell your license back to the government for, say, $1 million? And you can say whatever you want. You can say, no, you're not willing to sell for $1 million, that's fine. You will be kicked out of the auction forevermore. What does that mean? That means you're guaranteed to retain your license, you're guaranteed to stay on the air. But of course, you won't be getting any compensation either from the government, okay? Or you can say, yes, you would be willing to sell your license for $1 million. Doesn't necessarily mean that's going to be what happens, because it's totally possible that in the next round of the auction, you'll be asked another yes-no question, this time with a lower buyout price. Would you or would you not be willing to sell your license for, say, $950,000? Again, you can either say no and be kicked out forever, or you can say yes and live to see another day. If you're still in the auction when it ends, and I'll explain how it ends in a second, if you're still in the auction when it ends, then indeed the government will be buying your license, and the compensation will be the most recent, which is also the lowest, buyout offer that you ever accepted, okay? So that's the picture you should have in mind about this descending clocks auction. Everybody has these buyout offers, and they're decreasing over time. So how does the, oh, is there a question?
Seems like many people can refuse, and you will not get all the spectrum.
Good, so the question, I mean, it depends how high the buyout offers are. So, and that relates to my next point, which is how does the auction actually get started? And basically it starts by offering obscenely lucrative buyout offers to everybody, so that anybody would be ecstatic to sell their license at the opening buyout offer. Of course, these offers will be descending over time. But so for example, WCBS, which is the CBS affiliate here in New York, the opening offer for their license was $900 million for a single broadcasting license, which is kind of crazy. Now, if you were a station in Kansas, I guarantee your opening offer wasn't $900 million, but it would be something comparably lucrative given the context. Okay, so that's how the auction starts. How does it end? Well, intuitively, what the auction is trying to do is reclaim spectrum, a sufficiently large amount of spectrum, while hopefully paying as little as possible. So so what does it mean, clear sufficiently amount of spectrum? How do we measure spectrum? Well, spectrum, you can measure it in channels, each channel being a 6 megahertz block of the spectrum. So in the reverse auction, there is some target number of channels that you want to clear. Okay, so for example, you might want to clear 10 channels, which would be 60 megahertz of the spectrum. You could, for example, focus on the television stations currently broadcasting on the 14 channels between 38 and 51, and say, you know what, I'm willing to leave four channels on the air, but I really want to clear the other 10, freeing up 60 megahertz of spectrum, okay? All right, so a design decision that was made early on in the auction was that clearing a channel had to mean clearing it nationwide. So clearing channel 51 means at the end of the auction, there's literally not a single station in the nation broadcasting on channel 51.
On that frequency.
Yeah, on that frequency, exactly. Now, for that to be at all possible, it was crucial that the government used its power to unilaterally reassign stations' channel assignments. So I told you that if you drop out of this auction, you're guaranteed to retain your license, guaranteed to stay on the air, and that is in fact true. You're not, however, guaranteed to retain your channel assignment. Totally possible you are broadcasting on channel 51 before the auction, but after the auction concludes, you're forced to switch to channel 41. Okay, so the government indeed did that, okay, switched channels for a number of stations. So really, what the question is, what's the stopping criterion? What does it mean to clear enough spectrum? You want to buy out enough stations so that those who remain on the air can have channels reassigned to them so that they occupy a small number of channels, say only 4 channels out of 14, okay? So this is called the repacking problem, and to make sure it's crystal clear, let me show you a cartoon. So in this picture, each circle represents a television station. The area of the circle represents its broadcasting radius. The color of the circle, its channel. You'll notice that whenever you have two overlapping circles, they have different colors. Not an accident. Two stations with overlapping broadcasting regions have to be assigned different channels, otherwise there'd be destructive interference. Okay? So in this example, you can see that we're using 3 different channels, and indeed, it's easy to see that there's no way you could get all of these stations on the air without using 3 different channels. Because right here we have 3 mutually overlapping stations. So they alone would need 3 different channels. But remember, we're buying back some licenses. So imagine we bought out that gray station on the upper right. Then we'd be left with this picture, which maybe doesn't seem like much progress, because after all, we're still using 3 channels. But now we can recolor the circles. We can reassign channels so that only 2 distinct channels are used, freeing up the 3rd for sale in the forward part of the auction. So what this auction needs to do, it needs to make enough of the circles go away, that means buying back the licenses, so that the circles that remain can be colored with a target number of colors with no conflicts, so that overlapping circles get different colors. Okay? So that's what governs the stopping criterion. Okay? The prices go as low as possible, subject to clearing enough spectrum in this sense, that those who have dropped out you can repack in, say, 4 channels. There's a question.
Regardless of whether a station sells its license, all the stations got reassigned in this conversion from analog to digital. So it didn't, accepting the auction or not didn't make any difference to CBS, except that if they accepted it, they got a lot of money. They got reassigned a new channel anyway.
Sure, but they stayed on the air.
Yeah,
right?
but everybody stayed on the air.
So not over the air, right? So these are over-the-air television broadcasters. It's true they switched from analog to digital, so they're broadcasting digitally over the air, and they wanted to prevent some of them from doing that. That doesn't mean those channels don't exist. They could still be on a cable package, for example, but they're no longer allowed to broadcast over the air.
Unless they sold their license.
If they sold their license, then they're not able to do that. They're not allowed to use over-the-air broadcasting.
But they were given new channels in the digital spectrum.
Right, but okay. This part of the frequency, again, this is going to be prohibited because this is going to be going to telecom companies instead for different applications. Other questions? Yeah.
Given that the reverse auction was novel, how did the government know that the forward auction was going to clear a higher price than the reverse auction?
That's a very good question. So the question was about coordination between the reverse and forward auctions. And actually, to be honest, I've been lying a little bit to you. It's a little more complicated than what I told you. There's actually an outer loop. Okay, so I talked about clearing a target amount of spectrum, and one question you might have is like, well, where does that number come from? You just make that up out of thin air? So there's this outer loop which is searching for the right amount of spectrum to clear. So it started at 21 channels, 126 megahertz. That was round 1. And indeed, what the government would have paid in that reverse auction would have far exceeded what they would have made in the forward auction, okay, for that much spectrum. So that's why it went to a second iteration where they tried 18 channels, a third iteration where they tried 16. The 4th iteration was the successful one. They cleared 14 channels, 84 megahertz, and they were the numbers that I showed you. So that was the first iteration where the revenue covered the costs. Yeah, good question. Great. Okay. So this is the repacking problem. Make enough of the circles go away so that you can recolor the remaining circles in a target number of colors with a target number of channels. So some of you may recognize this as a very famous computational problem. This is basically the graph coloring problem. Okay, so a graph where you want to color the vertices of a graph so that any edge is bichromatic. Okay, so the different endpoints get different colors. And graph coloring is a well-known NP-complete problem. Okay, so it's not as tractable as some other computational problems, not as tractable as you'd like. So those of you who have some training in NP-completeness might be wondering, okay, so how did this auction cope with these NP-complete problems that are sort of fundamental to its stopping criterion? Maybe you're wondering, oh, is that why the auction took a year to run? That's not why. Okay, so let me tell you more about these graph coloring problems. So, NP completeness is not a death sentence. It doesn't mean it's impossible to solve the instances you care about in practice, but it does generally mean you need to up your game. Okay, you're not just going to write 10 lines of Python and have it work great on big instances. Okay, so your first question might be, well, how big are these instances actually? Maybe they're small enough so that NP completeness doesn't really kick in. And they're not huge, but they're not trivial either. I would call them medium-sized NP-complete problems. Think about graphs with maybe 2,000 vertices, 15,000 edges. That would be a representative size. So your next thought might be, it's like, oh, but come on. Like we have these incredible computational power these days, massive clusters. Take a day, take a week, whatever, solve your graph coloring problem. Okay? And that's a fine thing to think, but what I want to make sure is clear is that it's not that this auction has to solve just one graph coloring problem. It has to solve thousands of graph coloring problems every day, okay? I'll tell you why in a second. Given that, the FCC gave the team a budget of a minute for solving one of these graph coloring problems, and ideally with a common case being more like a second. And this now is a worthy algorithmic challenge for modern day, solving medium-sized NP-complete problems reliably in a second or less, okay? Not so simple. So why so many graph coloring problems? Well, so remember what this auction is tasked with doing. Okay? It has to buy back enough licenses so that everybody's left fits on a target number of channels. So the epic fail of the auction would be if it ever let enough stations dropped out so you could no longer pack them into the target number of channels. The auction can never let that happen. All right? So what does that mean? Well, remember, in each iteration of this auction, you go to a remaining participant, and if you want, you make them a lower buyout offer. Okay, that's how the auction proceeds. But before you make someone a lower buyout offer, you got to make sure you're ready for them to turn it down. They turn it down, they drop out of the auction, one more station you have to put on the air. Okay, if that's the critical station, that all of a sudden you need 5 channels instead of 4 channels to repack everybody who's dropped out, you cannot let them drop out. So the auction does not give them a lower buyout offer. The buyout offer just gets frozen at the most recently accepted one. Okay? So in every round of this auction, with every remaining participant, you need to do this speculative execution, which involves one of these graph coloring problems. That's why there's so many of them. Okay? Yeah.
So if you say yes at a certain price, at the next round you can't say no at that price?
No, you can say no. So you can only say no when there's a new offer that comes at a lower price than the previous one. Yeah, so accepting means I will accept forevermore at this price. No promises if you try to lowball me. Yeah.
Quote unquote collusion.
Okay. Right, so the first, so these are 2 different points, both good points. First point was that the order would seem to matter, and so indeed, within a round, this happens sequentially. You go through them one by one. So that was the first point, which is true. Collusion, so on the one hand, so one piece of good news is this auction has more collusion resistance than most auctions do. However, it's still not as strong as you'd want, and indeed in auction design, it turns out to just be very difficult to handle collusion inside the auction design framework. So usually that's handled separately by a legal channel. So it's just simply illegal to collude. Okay? And that's how you enforce it, through legal means, not through incentive means, or not through incentives internal to the auction means. Yeah. Yes.
Is it possible for the stations to directly sell to the telecom companies? And also, are these assignments, are they perpetual or do they have a sunset?
So the ones they actually sold in the forward version, I don't recall if they had a time deadline or not. I don't remember there being one, but I don't want to promise about that. As far as a secondary market for these licenses, there is one. It's sort of complicated. So different licenses have different terms for to what extent you're allowed to sell it to other people. So there's some licenses where you really just can resell them. A lot of them, you require FCC approval, in effect, to do the trade. So it's kind of, so there is a secondary spot market, but it's not, it's not doing reallocations at this scale by any means. Yeah. Good. Okay, so where were we? We were at needing to solve medium-sized graph coloring problems, typically in under a second. How are we going to do that? Well, the FCC made a good decision to bring on a computer scientist, Kevin Leighton Brown, who's a professor at University of British Columbia, to tackle this problem. So his team needed to solve these problems in under a second. And Leighton Brown team decided to stand on the shoulders of SatSolvers. So SAT here stands for satisfiability. That's basically given a Boolean formula, can you assign the variables to true or false so that all of the clauses or all of the constraints are satisfied. So why satisfiability? Because for decades, thousands of people have been working really hard to come up with better and better SatSolvers. There's literally even a workshop which is nothing but SatSolver competitions, which happens every other year. That's because they have a lot of important applications, okay? Not just here. So their thinking was, and also it's very easy to encode these graph coloring problems as satisfiability instances. It's a straightforward reduction. So as a benchmark, they said, well, let's just download kind of the best open source SatSolver and see how it does. And already that did reasonably well. So on representative instances, it was solving maybe 85% of them within the target budget of a minute, okay? But if you think about it, there's a pretty strong economic incentive to get that 85% as close to 100% as possible. Because what happens if your SatSolver times out after a minute? Okay? So what are you doing? There's a station, you're contemplating whether or not to make them a lower offer. You say, well, if they dropped out, could I repack them? And the SatSolver basically says, I don't know. Maybe you can repack them, maybe you can't. Don't know. So remember, the epic fail would be to be unable to repack everybody that's dropped out of the auction, so you have to be conservative when the SatSolver times out. You have to say, well, given that I don't have a proof that I can repack them, I have to assume that I can't. Therefore, whenever you have a satisfiable instance that your SatSolver fails to solve, that is literally a huge pile of money left on the table. Okay, that's a station you could have afforded to make a lower offer to, but you didn't just because your algorithm wasn't good enough. So I don't know about you, but I mean, this is pretty much the most direct linear relationship I've ever seen between the running time of an algorithm and huge piles of money. So kind of interesting. All right, so they did, the happy ending is they did get, more like 99+% of the instances within the target amount of time, within a minute, and usually within a second. And there were basically two ideas that they used to get up to 99%. So the first one was to do what you often do when you have to solve NP-complete problems in practice, which is you build in domain knowledge. You stop worrying about solving every satisfiable instance in the world, and you start tuning your solvers for the instances you expect to see. And in this application, the team knew a lot about these SAT instances in advance. They knew exactly which stations were going to be in the auction. They knew what their broadcasting regions were, so who interfered with whom, and so on. So all of these graph coloring problems were basically induced subgraphs of a sort of master graph. So the first thing they did is they built that domain knowledge into the solvers. The second thing they did, which was really clever, is they had a number of caching tricks. This allowed you to reuse computations from previous graph coloring problems for future ones when they were sufficiently similar. And those were the two optimizations that got them up to 99%. Okay? So let me say one last thing about the reverse auction before moving on to the forward auction. I want to show you how this novel economic design actually motivates a basic, purely algorithmic question. So this is now the flow of ideas going backward to computer science. So to explain, let's think about this auction as basically a heuristic algorithm for a difficult optimization problem. What's the optimization problem? Well, you have a constraint on how many channels you can put stations on. Subject to that constraint, you want to maximize the values of the stations you put on those channels. Implicitly, we're sort of hoping that the outcome of this auction is going to be a reasonable solution to that optimization problem. So Milgram and Segal, among the many cool properties they proved about descending clock auctions, they characterized exactly which heuristic algorithms can be implemented as a descending clock auction. Okay, some can and some can't, and they characterized exactly which ones can. And it's a class of algorithms known as reverse greedy algorithms. So let me just explain that with an example. Okay, so one famous computational problem is the minimum spanning tree problem. I give you a graph, each edge has a cost. Your goal is to compute a spanning tree of the graph to minimize the sum of the edge's costs. Okay? So if you study undergrad algorithms, you learn something called Kruskal's algorithm, which is a forward greedy algorithm, where you greedily add edges subject to feasibility. So you do a single pass through the edges from cheapest to most expensive. You always add an edge as long as it doesn't create a cycle. But you could equally well do a reverse greedy algorithm, where you greedily delete edges from the graph. This would be a single pass from most expensive to least expensive, and you delete an edge unless it disconnected the graph. Okay? For minimum spanning trees, and more generally for a family of problems known as matroid optimization, both of these algorithms are optimal. Both of them will do exactly the right thing, and they're therefore equivalent to each other. But the plot thickens if you go just a little bit beyond matroid optimization problems. So even if you just go to something as simple as bipartite matching, you can take some natural, simple, forward greedy algorithm with a good performance guarantee. If you run it backwards, it can be a complete disaster. Okay? And that's true in particular for problems as simple as bipartite matching. So this observation led me and several former postdocs to systematically study the power and limitations of reverse greedy algorithms. What can they do? What can they not do? Okay, so for example, we designed more complicated reverse greedy algorithms that did match the performance of their forward counterparts. Okay, so you can do well with reverse greedy algorithms, you just have to work a little harder. But remember, the reason we wanted a reverse greedy algorithm is because that's exactly what you can embed into this descending clock auction framework. Okay? I guess one final comment here, just the high-level point, right? So before our work, it's not like no one had ever thought about reverse greedy algorithms. There was a scattered paper here and there, but nobody ever, frankly, really cared, right? They just seemed like more awkward than their forward counterparts and didn't seem to do better, so why bother trying to design reverse greedy algorithms? So here, coming from economics of all places, is the first extrinsic reason to care about the class of reverse greedy algorithms and what they can and cannot do, which turns out to be a completely basic algorithmic question. All right, so any questions at this point before I move on to the forward auction? Oh, yes.
I don't understand why it had to be done in a second. Don't these stations have a week or so to decide whether they're going to accept it?
No, they were doing, at the beginning of the auction, they did 2 rounds a day. And then as people dropped out, they actually jacked it up to 3 rounds a day. And you started with about 2,000 participants.
Don't they have a minute or 2?
Right, so good. So this is sort of a user interface question. So the way they actually implemented it, so the rounds started at prescribed times, like 10 a.m., noon, 3 p.m., whatever. And so what they did is that everybody who was still in the auction, they basically had to pre-announce if, Okay, so first of all, the decrements, the extent to which they decrease over time was known. It was 5% each round. So you know what your current buyout price is. You already know what your next lower one would be if you had one. So you pre-ask everybody, if it came to the point where we needed to make you a lower offer, would you or would you not accept it? And then everybody sort of pre-answers that question, and then they run the sequential algorithm under the hood. So there's a lag time of sort of a few hours between rounds from the bidder's perspective, but because in between those rounds you had to process thousands of these graph coloring problems, you really wanted it to be a second. Yeah, good question. Oh, yes.
Going back to the earlier question, I just want to know, is there an optimal sequence to this, or what is the optimal order?
How to order them?
What is the algorithm for that?
Good question. So this is following up on the point that the order matters. So I wasn't a member of this team, so I don't know exactly what they did. I asked them point blank. They didn't tell me what they did. They promised me they didn't do anything too smart. So I don't know if they chose a random order every round. I don't know if they used a fixed order every time or what, but my guesses would be something like that. They did come up with a really clever idea, unfortunately just a little bit too late to make it into the implementation, which was what you basically would process them in order of how easy their repacking problem is. So you just fork 2,000 threads to solve everybody's repacking problem if they were the first one to drop, if they were the first one asked. And whoever finishes first, that's who you make first in the round. Okay, but that didn't actually make it into the implementation. So, yeah. That's a good question. I don't know. Yeah, so the question was, are the SatSolvers failing more on satisfiable instances or unsatisfiable instances? It's the satisfiable instances where it really breaks your heart when they time out. But you might guess that it was mostly unsatisfiable instances where it failed. But I don't know the data on that. Yeah, good question. There's another question over here? Yes.
Was it 5% decrement in price every round?
That's my recollection, yeah.
Okay.
Yeah. Given that it went for a year, there's some second guessing that maybe it should have been a bigger percentage. But yeah, that's one of the knobs you have to sort of control the length of the duration of the auction. I believe it was 5%. Yeah. So in other words, once you know your opening, once the opening buyout offer is set, you know what the entire sequence is going to be. Yeah. All right, forward auction. So now the government has all these licenses, wants to sell them to the highest bidder, okay? Now remember, these are the auctions that have been around for a long time, since the early to mid-90s. So computer science was sort of too late to the game to have much influence on how these were designed, but we'll see that computer science language is perfect for articulating when these work well and why. So it's actually kind of a stressful job designing spectrum auctions. As we've seen, the stakes are high, and it turns out it's really easy to screw them up. And debacles have happened. And a famous cautionary tale is from New Zealand in 1990. This is before governments really had much experience running auctions. So New Zealand decided to create 10 new nationwide television channels. Okay, so 10 licenses, basically interchangeable, and decided to sell these via auction, which is not in itself a bad idea. For reasons sort of been lost to the sands of time, they chose a rather peculiar auction format to do it, which I would call simultaneous second price auctions. Okay, so what's a second price auction, also known as a Vickrey auction? Well, so this is for a single good. This is like what happens on eBay. So the way it works is everybody bids, the highest bidder wins, but the winner doesn't pay their own bid, but rather the highest bid by some competitor, so the second highest bid overall. And if you've ever won an eBay auction, you know that's exactly what happens. If you type in $100 for your bid, it's usually not what you have to pay if you win, you just pay high enough to beat out everybody else. So second price auctions are practically useful and theoretically beautiful. They have great properties, like there's no reason to be strategic. It's a dominant strategy to just bid whatever your maximum willingness to pay is. But all of these nice properties melt away if you run a bunch of these second price auctions in parallel, like they're running 10 in parallel here. And indeed, think for a moment. I mean, what if you were a bidder in this auction? You wanted a license, only one license. You can submit up to 10 different numbers, one on each of the licenses. Each license is sold to the highest bidder on that license at a price of the second highest bid on that license. What should you do? And the point is that's not a very easy question to answer. One strategy, defensible strategy, is pick a random channel, lucky channel 7, and bid your maximum willingness to pay on the one channel. All your eggs in one basket. Another strategy, which especially if you didn't think there were that many other bidders in the auction, might be a good idea, would be to go bargain hunting and submit a really low bid on lots of channels, hoping you get lucky, and on one of them you get it for a really low price, okay? And a good rule of thumb is that whenever you have an auction where it's highly unclear what participants are supposed to do, it's probably going to be an auction where there's a lot of unpredictability in the outcome, and in particular, could be vulnerable to bad outcomes. And that was the case in New Zealand. They were hoping to make $250 million from these 10 licenses. That'd be $25 million per license. It didn't quite work out for them. They got less than 15% of that, okay, $36 million. And moreover, if you actually look under the hood and look at the details, you can find some pretty cringe-inducing facts. Like there was one license where the high bid was $100,000. So you already know, nightmare. They were hoping to make $25 million. I'm telling you, the high bid was $100,000. The second highest bid,
These were all interchangeable licenses?
all interchangeable. As far as I know, it's a first order interchangeable. Yeah, it's a crazy way to sell them, yeah. It's a good thing we don't do, like treasury auctions this way. Okay, so, right. So this one channel, the high bid was $100,000, already complete fail. The second highest bid, and therefore the selling price, was 6. Not 6,000. Someone got a license from this auction for $6. Okay? So, fast forward to the modern day, right? These are, people are using governments are using forward auctions all the time. What do? What do the best practices look like? Well, a lot of bells and whistles have been added over time, but especially in the US, the workhorse remains the original format proposed to the FCC in the early 90s called simultaneous ascending auctions. So you all are familiar with a normal ascending auction for a single item. That's what you see in the movies. If you walk down the street to Christie's, that's what you'll see at an art sale there. Right? There's an auctioneer that keeps naming higher and higher prices. You raise your hand as long as you're willing to pay it. The auction ends when there's only one person left with their hand up, and the selling price is whatever the most recently announced or highest price would have been. So that's for selling one item. We care about selling multiple items because we have multiple spectrum licenses we're trying to allocate, but nothing's stopping us conceptually from just having one auctioneer per item. And so now as a bidder, you raise your hand in a subset of the auctions of your deciding. And again, each auction is sold, each license is sold in the usual way. Okay, so a license is sold when there's only one person with their hand up on that license for the most recently announced price on that license. Okay? All right. So those are simultaneous ascending auctions. And this is the workhorse of what people use. That said, it's not like anyone thinks these are perfect without flaws. So let me tell you about two of the well-known issues that simultaneous ascending auctions suffer from. Okay. So the first issue is something known as demand reduction. And this is going to be easiest to explain with an example. Okay? So let me pick on Afonso. Let's say there's just two bidders, me and Afonso, and there's two items, two licenses. Let's say a license for Pennsylvania and a license for New York. Let's say Afonso would be happy to pay 6 for Pennsylvania, happy to pay 6 for New York, happy to pay 12 for both. Let's say I'm a much smaller bidder. Okay, I only want one of the licenses. I don't care which one. I'd be willing to pay up to 5. Now, it's clear what we want to see happen. Right? We'd like to see Afonso get both of the licenses because he has higher value than I do for both of them. Right? So he should just get both. So what's going to happen in a simultaneous ascending auction for these two licenses? Well, I'm going to be kind of a pest because I'm not going to go away. I'm not going to drop out of the auction until the prices for both licenses hits 5. Because I'd be happy to take either license for a price less than 5. So Afonso can stick around in the auction and wait till both prices hit 5. At that point, I'll drop out. He'll win both of the licenses. He'll get a value 12 for them, pay 10, utility of 2. Okay, so that seems like a win. But if you think about it, there's something smarter Afonso could do, which is he could just concede Pennsylvania to me. Never bid on it. I'm going to get it basically for free. Right? There's no competition. I only wanted one license, so I'm not going to bother bidding on New York, and Afonso will get New York for free. So this gives him a value of 6 because he only has one license, but now he pays basically nothing. So the utility has jumped from 2 to 6. So that is demand reduction. That is when bidders bid for fewer items than they rightfully deserve in order to get them for a much cheaper price.
But that was collusion.
Yeah, so it could be. I mean, well, if I knew his preferences in advance, then it's something you could implement. Yeah, but if you didn't, it would be a dangerous strategy, no doubt. Yeah. So obviously, I mean it just as a toy example, needless to say. Okay, so the second problem arises in the special case where there are strong synergies between items, also called complementarities. So let's keep my preferences the same as before, but let's say Afonso just wants to go big or go home. He's willing to pay 6 if he gets both Pennsylvania and New York, but he has 0 for anything else. He doesn't want just one of the licenses. Okay? If you think about it, we still want Afonso to get both of the licenses. You can only make one of the two of us happy. He has the higher value, so he should just get both of the licenses. But again, in a simultaneous ascending auction, I'm not going to go away until the prices of both hits 5, at which point the combined price of 10 would be more than Afonso's value for that pair of licenses. So literally, in this case, Afonso's best strategy is to just walk away from the auction and not even play, okay? Despite the fact that in some sense he's the one who deserves to have the licenses. So that's the exposure problem which arises when you have synergies between items. Okay, so how big a deal are these flaws with simultaneous ascending auctions? Well, if you ask around, people in the trenches, so people who design these kinds of auctions, people who advise, consult for the bidders in these auctions, you get a reasonable consensus around 2 sort of folklore rules of thumb. So the first rule of thumb is that in that first example, so when you don't have item synergies, simultaneous ascending auctions, they're not perfect. They suffer from demand reduction, but the thinking is that the loss of welfare or efficiency from demand reduction, we can live with it. Okay, so you don't get a perfect allocation, but you get a pretty good one. Okay, much better than if you hadn't run the auction at all. Okay. On the other hand, and this is the second rule of thumb, if you do have strong item synergies, then indeed the exposure problem can be a really big deal. Okay, and there might be a large amount of efficiency loss from the exposure problem with such a simple auction format, simultaneous ascending auction. So the thinking there is you really need to add significant complexity to the auction if you're in the presence of strong item synergies. Okay, so neither of these two rules of thumb are new. They've both been around, 20 years. And as you can imagine, auction theory has a very rich literature, okay, over a half century old. But despite all that, at least to my knowledge, I don't know of any theorem in the economic theory literature that maps onto either of these two folklore beliefs very directly. Now, I do have a theory for why, which is, if you think about what would a theorem look like that made these sort of beliefs rigorous, I claim it would fundamentally be a theorem about approximation. A theorem for the first one would say that, the outcome of some simple auction would be in some sense good, some sense close to optimal. Whereas the second one is saying it's not close to optimal. Again, no one's saying these auctions are optimal. Nobody thinks that. But in the first case, you're close to optimal, and the second one, you're not. And for whatever the reason, it's just not part of the economic theory tradition to prove approximation results of this type, to prove approximation guarantees in the presence of suboptimality. And so by contrast, in computer science and operations research and other fields that have been coping with NP completeness for decades, we have to reason about competing heuristic algorithms. And one of the ways we do that is through the formalism of approximation guarantees. And that exact same formalism will be perfectly suited for making these rigorous. And that's what I want to talk a little bit about in my remaining time. So let's start with the first one. Yeah, there's a question.
I may be wrong, but it seems to me that some of these problems may go away if this problem of simultaneous auctions. If you just take time and do it sequentially.
Sequential auctions have some serious problems. Yeah, the thinking is that best practices is actually simultaneous, not sequential. We can talk about it, but you get some really weird game theoretic behavior in the sequential case. Yeah, there's just a lot of ways to, implicitly collude and implicitly influence people. So there's a long list of reasons why people do like the simultaneous case. Yeah. Good. So first point. So the belief is that if you don't have strong item synergies, simple auctions can work pretty well in some sense. So, okay, the outcome of an auction. So don't forget, bidders are strategic. They're going to bid in their own best interest, given the rules of the game you set up with your auction format. So when we speak about the outcome of an auction, what we really must mean is an equilibrium, like a Nash equilibrium, in the game induced by the auction that was chosen. Okay? So what we want for this first theorem is it should be an approximation guarantee, a near optimality guarantee, for the equilibria of some game. So this is great news, it turns out, because since the beginning of this kind of surge of research on the computer science economics interface 20 years ago, lots of people have been thinking about exactly this, approximation guarantees for Nash equilibria and variations thereof. The key concept here is the colorfully named price of anarchy. That was called so by Koutsoupas and Papadimitriou in '99. That literally just means what fraction of an optimal objective function value is attained by equilibria. So it's measuring the suboptimality of equilibria. It's a concept I was totally obsessed with when I was a graduate student. It's what my thesis is all about. And if you saw Christos or me or anyone else give a talk about it around that time, the slides probably would have been littered with pictures like this, pictures of networks, because we were all kind of obsessed with the internet when we were first thinking about the price of anarchy. But if you fast forward to present day, I'm happy to report that there's now a very mature and powerful analytical toolbox for deriving price of anarchy guarantees, approximation guarantees, even for very complex settings, including the types of auctions we're talking about today. So let me tell you a little bit more about that. To state a theorem formally, I kind of need to tell you a little bit about a model. So let me just put one slide saying, what is the mathematical model people use to reason about outcomes of multi-item auctions like spectrum auctions. All right, so we've got our bidders, again, T-Mobile, AT&T, et cetera, n of them, let's say. There's some number of items, m, for us that's how many licenses we're selling. Bidders have preferences. So how are those described? They're described with what's called a valuation. Okay, so for each bidder, it has what's basically like a huge lookup table of length 2 to the m, where m is the number of items, where an entry in this lookup table is specifying its maximum willingness to pay for that particular subset of items, subset of licenses. Remember, there's m licenses, so there's 2 to the m subsets of licenses you might receive. You can have a different willingness to pay for each of those subsets in general. Okay, so now naturally a bidder wants licenses for which it has high value. It also doesn't want to pay very much. So the simplest utility function is so-called quasi-linear utility, where you assume that each bidder bids in order to maximize the difference between the value of the licenses they receive minus what they have to pay for them. The final ingredient we need in the model is an objective function to assess the quality of an auction outcome, like an equilibrium. And in this part of the world, the usual objective function is known as the social welfare. And the goal here is just to make everybody as collectively happy as possible. So the assumption is that in a perfect world, what you'd like to do is partition the m items amongst the n bidders to maximize the sum of their valuations, okay, with each item going to only a single player. Okay? So when we speak about an auction performing well, what we're going to mean is that it achieves social welfare not too much less than this utopian benchmark of the maximum possible social welfare over all allocations. Okay? All right, so in this model, researchers in algorithmic game theory have proved many different versions of that first folklore belief, that without strong item synergies, in fact, provably, simple auction formats do pretty well. The reason there's a long list of papers here is that there's a lot of different ways you can define without strong complements. There's a lot of different simple auction formats you might want to think about, and there's many notions of equilibria. But so for sort of all of the combinations you might care about, we know good approximation guarantees for simple auctions. I'll give you a concrete version of one of these on the next slide, just to make this a little more concrete. Proofs I won't have much time for, but let me at least mention a little bit about what's the strongest common theme throughout all this work, or a proof technique if you like. It's something I like to call smoothness arguments, or alternatively extension theorems for smooth games. And it includes definitions and theorems and so on, but I really think of smoothness arguments more as a philosophy, a kind of two-step recipe for generating good price of anarchy bounds for very complex settings like these. So step one of the recipe is you just make your life way easier with simplifying assumptions. So you say, for example, usually players are allowed to randomize in a game, but you say, no, I don't want to deal with that. Let's just assume players play deterministically and look at pure strategy Nash equilibria. Usually in an auction context, you want to look at Bayes Nash equilibria. You want to assume there's uncertainty in bidders' valuations. Again, too complicated. Let's just sort of fix valuations for everybody and do full information analysis. So step one is to prove some kind of price of anarchy guarantee in that simple setting, okay, with all those extra assumptions. Step two is then apply an extension theorem which lifts that approximation guarantee with no loss to the complex setting being like mixed strategy Bayes Nash equilibria, something like that. Now this should strike you as too good to be true, right? So how do you just automatically sort of extend the result from a special case to the general case? In general, it is too good to be true, but, and this is the key point, it's possible to impose conditions on how you prove an approximation guarantee in step one in the simple setting, so that as long as your proof conforms to this prescribed template, then in fact the guarantee you prove does lift with no degradation to the complex setting. And it turns out that's sufficient for almost all of the main results in these papers, following that two-step recipe, okay? All right, so let me just, again, this might be a little abstract, so let me just sort of give you a precise statement, one example of this line of work. All right, so again, the punchline is without strong item synergies, simple auctions do pretty well. So what do I mean without item synergies? A fairly permissive definition is that of subadditive valuations, and that means just what it sounds like. Okay, so it means that your value for the union of two bundles should be no more than the sum of your values for the bundles individually. If you go back to that example with me and Afonso and the exposure problem, Afonso's preferences exactly violated this inequality. Remember, he had value 0 for New York, 0 for Pennsylvania, but value 6 for the pair. Okay? So this restriction is getting rid of the exposure problem in that sense. So a very pretty theorem of Feldman, Fu, Gravin, and Lussier, this appeared back in Stock 13, they said, well, let's consider one specific simple auction format, simultaneous first price auctions. You can tell a similar story for other auction formats as well. And so what they proved is that even in the worst case over all possible subadditive bidder valuations, and even in the worst case over all equilibria of the induced game. Remember, games usually have multiple equilibria. So for every equilibrium of every game induced by subadditive valuations, the equilibrium extracts a constant fraction of our utopian benchmark of the maximum possible social welfare that is guaranteed at equilibrium. The constant fraction, the magic number in this case, turns out to be 50%. That's a worst case bound. It's tight in the worst case. Of course, you'd expect it to be higher in most cases. If you make stronger assumptions, you can even get a better worst case bound. If you instead assume that evaluations are monotone and submodular, the 50% jumps to 63%, which again is tight in the worst case. So I offer you this as one of the many ways in which the community has made precise this idea that without strong item synergies, simple auctions work well. So in my remaining few minutes, let me say a little bit about how to turn our second folklore belief into a rigorous result. So our first result was a positive result. It had the flavor of algorithms. The second result is an impossibility result. So it has the flavor of complexity theory. Okay? All right. So we want to say that when there are strong item synergies, simple auctions need not do well. Okay? They're vulnerable to extremely poor outcomes. So the first sanity check you might do is you say, well, let's look at the same auction format that worked so well for us earlier, simultaneous first price auctions. Let's just drop the subadditivity assumption and see what happens. Maybe they still work well. Well, they don't. Okay, so that was proved by Hasidim et al. And what they showed is that if there are strong item synergies, then equilibria of simultaneous first price auctions are not guaranteed to get even 1% of the maximum possible welfare, not even 0.1% as you scale up the number of items. And the bad examples are not even very pathological. It's literally just that example with Afonso and me with the exposure problem scaled up to a larger number of items. So it's a total disaster. But this isn't that satisfying, because who said we had to use simultaneous first price auctions? What if we use simultaneous second price auctions? What if we allow bidders to bid on pairs of items, not just on individual items? What if we're smarter? Well, it turns out that there's a general impossibility result, which is that when there are strong item synergies, when valuations are unrestricted, in fact, no simple auction can guarantee 1% of the maximum welfare at equilibrium, or 0.1%, or 0.01% as the number of items grows large. Okay? Now, what you should be wondering is, there's sort of an undefined term in this theorem, which is, what is a simple auction really? Right? For our positive result, I didn't need to define this. I just said, let's just fix one simple auction and prove something about it. To rule out everything, I need to say, what's the class of auctions I'm looking at? And for the purposes of this result, I can use a very permissive definition. I can describe it in terms of the number of bidding parameters. So in something like simultaneous first price auctions or simultaneous second price auctions, there's M bidding parameters, where M is the number of items. Right? As a bidder, you're allowed to submit up to M numbers, 1 per item. If I also allowed you to bid on pairs of items, that would jack up the bidding parameters to like M squared. So for the purposes of this theorem, any auction with a sub-exponential in M number of bidding parameters qualifies as simple and is subject to this impossibility result. So even if you elicit 2 to the root m numbers from everybody and process those 2 to the root m numbers in arbitrarily clever ways, it doesn't matter. There will be equilibria with arbitrarily poor welfare. So I offer you this as a formalization of that second result. Without so when you do have strong item synergies, in fact, simple auctions just aren't good enough, okay, to get good welfare guarantees. You have to add a lot of complexity to the auction. Okay, so I don't have a lot of time to talk about the proof of this result, I will say that the proof fits on a single slide, and here's your slide. Maybe I'll just say a little bit about, morally why this theorem is true, what makes the proof work. Okay, so the way the proof works is it's actually a translation, a black box reduction from lower bounds in one computational model to lower bounds on equilibria of simple auctions. It turns out the relevant computational model, it's a fairly esoteric one, but it turns out to be perfect for this application. It's known as non-deterministic communication complexity. So it's the study of communication protocols, which don't use too much communication, but non-determinism means they're also allowed to have some all-powerful prover giving them advice about what they should do. So what the general theorem says is that whenever you have an impossibility result for these non-deterministic communication protocols, you automatically get exactly the same impossibility result for the price of anarchy of arbitrary simple auctions. Okay, so that's the way it works. So basically, from a too good to be true price of anarchy bound, the proof extracts a too good to be true non-deterministic communication protocol. And the reason you can do that is because equilibria have two properties that make them not much more powerful than more familiar objects like polynomial time algorithms or polynomial communication protocols. Number one, equilibria are guaranteed to exist. I'm thinking of mixed Nash equilibria here, so Nash's theorem tells us there's always at least one. The second property is easy verification. If I handed you an alleged Nash equilibrium on a silver platter, it is not difficult to check my claim. You just check the best response condition for each of the players. So these two properties, guaranteed existence and easy verifiability, is what limits the power of equilibria to be bound by the same limitations as non-deterministic communication protocols. Okay, at the beginning of the talk, I asked how does computer science inform modern auction design? I hope in our time together you learned a number of satisfying examples. In the novel reverse auction, we saw the auction format itself drew on computer science, and also techniques for coping with NP completeness were completely fundamental to that auction. Without techniques from computer science, the government literally would have had to run a different reverse auction. They could not have used the format that they used. Meanwhile, in the forward auction side, we've seen how price of anarchy bounds explain when they work well, and how complexity theoretic impossibility results explain when they don't. So that's all I've got. Thanks very much.